Welcome to the second lecture of EE557 of this week. In the last lecture, we have started with a new topic called finite state Markov chains and controlled Markov chains. In this lecture, we are going to continue with that topic, and we are going to see some probability calculations, and then we're going to investigate the resulting probability formulas that we get. So remember, when we talk about a Markov chain, we think about a state inside a finite set, okay? And for defining a Markov chain, we first specify an initial distribution. So I have the initial P0 vector. This is in Ri. And we also define a probability transition matrix. This is in R, I by I. All right? If the Markov chain has an input, then this is the no input case. And we have, when we have an input, then this probability transition matrix is dependent on UK. In that case, we see that depending on U, the transition matrix of the Markov chain changes. So when UK changes, we are going to actually get a time-varying Markov chain. So we are going to, at the end, control the Markov chain by changing those UKs, either open loop or closed loop. And in order to be able to do that, remember we defined a cost function which actually calculates the cost of state of the Markov chain being at xk and the input being at UK, okay? And we would like to minimize this cost function over a horizon from k equals to 0 to n, and because this is a random quantity, what we do is that we take the expectation of this one, and we would like to minimize this cost function with respect to the input or the feedback loop, depending on we choose the open loop control or the closed loop control. Remember that we have seen in the earlier lectures that closed loop control is much more powerful in this stochastic case than the open loop control. Okay? So here the task is first how to calculate this objective function or this cost function. See that that cost function requires the expectation of some functions. So here, let us simplify this problem a little bit. Suppose that I can choose UK either as deterministic, so this would remain like this, or I can choose UK. In this case, this minimization is with respect to U from 0 to n. And if I look at the closed loop case, then I have xk, gk, uk. And I minimize this with respect to g0, n. Okay? Sorry, this is gk, xk. Okay? And this is the closed loop case. Open loop, closed loop. In both of the cases, we need to take the expectations with respect to xk. Okay? So here, you see that UK is deterministic, and only stochastic component here is xk, and therefore this expectation has to be taken with respect to xk. Here, on the other hand, there is no non-random component. Both of the components are dependent on xk, so both of the components are random here. Therefore, I need to take expectation again with respect to xk. Okay? So here I can generalize this problem. Given any function of c of xk, how can I take its expected value given the Markov chain parameters? Okay? This is not really a difficult problem. If you have seen a probability theory in the past, I think this is going to be easy for you. So here, this is an expectation. Remember, if I had a continuous random variable, then the expected value of c of xk can be taken as p of xk dxk. This is the continuous case, and when I have the discrete time case, this integral is going to be a summation, and instead of xk's, I can put the indices of xk's here from 1 to I. Okay? So in this case, I don't have the continuous case, but let us write the discrete case. So the xk can take values I from 1 to capital I, and here I will write Ci, and then I will multiply this with the probability of xk is equal to I. Okay? We see that this is nothing but the probability mass function of, so if I call the probability mass function of xk as just P of I, then this would be that times C of I. So this is like an integral C of xk, P of xk, dxk. Okay? So we see that this expectation is just a finite summation here. So here I would like to use some vector notation in order to write this expectation using some vectors. Okay? So here is what I'm going to do. I will write P of xk is equal to 1, P of xk is equal to 2, going until P of xk is equal to capital I. I will put them into a vector, and I will write this vector C1, C2, going until Ci. So we see that this is like an inner product. Then this multiplies this with this probability, and plus multiply this and this, plus, etc., and I would get this summation. Now this is nothing but the probability mass function of the state xk. Okay? So I will just call this vector just as pk. This is similar to this p0. P0 is a horizontal vector containing the probability mass function of the state x0, and here this is nothing but pk, which contains the probability mass function of the state xk, and I will say that this is the vector c. Okay? So that gives us the expected value of C of xk is nothing but pk, which is my horizontal vector, times C, which is the vertical vector containing the values of C inside. Okay? So that is our final formula. So I turned actually the problem of calculating the expected value into a problem of calculating this pk. Okay? So currently I don't know what pk is. I always know what c is. Just take this cost function and substitute xk is equal to 1, 2, 3 until I, and obtain the c vector, and calculate the pk vector somehow, and then multiply these two vectors to calculate the expected value. Okay? So now the question is, how do we calculate this pk? We know that this pk contains some elements, pk1, pk2, going until pki, and I would have each of these elements are pki are the probabilities. Probability xk is equal to I. Okay? So this is nothing but PMF of xk. All right? So now how do we calculate this pk? How can we calculate pk? The problem turns into this problem. And what are we given here? We are given P0, okay, that is the initial probability, initial state distribution, and this has components P01, P02 going until P0i, okay? And we are given the TPM of the Markov chain, okay? And this is composed of Pij's, and each Pij is probability xk plus 1 is equal to j, xk is equal to I, all right? Given this, I need to calculate this vector, horizontal vector pk for k is equal to 1, 2, 3, etc. So a very useful idea here is to calculate pk recursively. Okay? So let us calculate pk recursively. Okay? So how can we calculate, pk plus 1 from pk? If I know how to actually calculate pk plus 1 from pk, then because I know p0 here, I can calculate p1 from it by substituting k equals to 0. And I can calculate, by substituting k equals to 1, I can calculate p2 from p1, etc. In this recursive manner, I can calculate all of the pk's. So the task is to calculate pk plus 1 from pk. Let us write the vector pk plus 1. It is again composed of some elements, pk plus 1, 1, pk plus 1, 2, going until pk plus 1, I. Alright? And each of these pk plus 1 j's, they are equal to the probability of xk plus 1 is equal to j. Okay? Now I have to find the relationship with these probabilities, with the probabilities inside pk. Okay? Let us try to do that. So I'm going to start with this expression. Pk plus 1j is equal to this. Now I'm going to use the total probability theorem. So this is I from 1 to I, okay? And that is going to be probability xk plus 1 is equal to j, comma means and, the intersection of these two events, xk is equal to I, okay? This is the joint probability of these two events, and if I sum this over the second argument here, I would get this one. Now I am going to use some conditioning idea. This is equal to I from 1 to I, P of xk plus 1 is equal to j, given xk is equal to I, times probability xk is equal to I. Okay? This is just using the conditioning formula. This conditional probability is nothing but this joint probability divided by this marginal probability. So this joint probability is nothing but this conditional probability times this marginal probability. Okay? But this is nothing but my transition probability, Pij. Okay? And this is nothing but the ith element of the vector pk. This is pki. Okay? So we get the formula I from 1 to I, Pij, Pki. Okay? Now I can write this in a neat way. Pk plus 1j is equal to, I have I from 1 to capital I, Pij times Pki. That is my formula. And this is true for which values? This is true for any j. This is true for j is equal to 1, 2, going until I. All right? That is my main recursive formula. So you see that I now express each element of this pk plus 1 vector in terms of the elements of pk vector and the transition probability matrix. So here is what I'm going to do. I need to use some vector matrix multiplication operation instead of the right-hand side summation there. Okay? In order to be able to do that, I would like to remind you the following. Suppose that I multiply two matrices, A and B, and suppose that I would like to calculate the mth row and column element of that multiplication. Okay? Then this is given by I will just write here I from 1 to some elements, and actually I will not write the elements here, the number of elements. So this is going to be a summation of with respect to I, and I would have A mi and B in. Okay? This is what the matrix multiplication makes. If you would like to calculate the nth row and column element of a matrix multiplication, then that is given as a summation like this. You need to use the mth row of A, and you need to use the nth column of B, and you need to take their inner product, okay, whatever their sizes are. All right. So now I would like to write this formula in that manner. Okay. I know that this Pij is nothing but ijth element of the TPM, transition probability matrix, and I will write this Pk plus 1j. Pk plus 1j is nothing but, remember, Pk plus 1 vector is a 1 by I vector, okay? So its jth element is nothing but first row and the jth column element, okay? And what about Pki? Pki is similarly the first row and the ith column element of Pk. Okay? Now let me write all of these into their respective places there. So I have Pk plus 1j is nothing but Pk plus 1j is equal to summation I from 1 to capital I. Instead of Pij, I will write P ijth element, and instead of Pki, I will write just this, Pk 1I. Okay? Now I would like to turn this summation into something like this. Okay? I want the row element to be determined, so I will just take this, I will just replace these elements like this. So I from 1 to I, so this is Pk 1I and Pij. So you see that we are calculating the first row jth column element of Pk plus 1. So then I have here, these ones are the same and these j's are the same. I's are in the middle. Okay? So you see that this is therefore a matrix multiplication of this form. Okay? So here, then I can write the result. Pk plus 1 vector is nothing but this Pk vector times the matrix P. Okay? So this is our recursive update formula for the Markov chain state distributions. If we know Pk, then in order to be able to calculate Pk plus 1, I multiply that horizontal Pk vector with the transition probability matrix from the right, and the resulting vector becomes the state distribution of xk plus 1. Okay? So that is our recursive formula. Now I can answer the question, what is P1? What is the state distribution or probability mass function of P1? It is P0 vector times P. What is P2? Then it is going to be I would have P1 times P, but P1 is P0P times P, but it is P0 times P squared. Okay? And I can continue in this manner to write Pk. Pk is going to be P0 times P to the k. Okay? That is our formula that would express the state distribution Pk in terms of P0 and the transition probability matrix of the Markov chain. Okay? So we get Pk is equal to P0 times P to the k. Okay? And for this expected value, all I need to do is to multiply this Pk with this C vector. So that means that expected value C of xk is nothing but Pk which is P0 times P to the k times C. Okay? So that is my resulting expected value given by the parameters of the Markov chain, initial state distribution, and I would have here my transition probability matrix to the power k, and this is the cost function vector C here. All right? Of course, these formulas, they are correct for k larger than or equal to 0. Okay? So now I will just write a remark and I will talk about this matrix P to the k. Okay? Remark. Note that using the same derivation, we can write the following. P L plus K is equal to PL times PK. Okay? And this is true for L larger than or equal to 0 and K larger than or equal to 0. Okay? So what is this? This is the state distribution, PMF of XL. This is the PMF of XL plus K. Okay? So this expression is doing nothing but writing the distribution of XL plus K from the distribution of XL. Okay? So this PK is nothing but the probability transition probability matrix, but it is not one-step transition probability matrix. It is k-step transition probability matrix. Okay? This means that P to the k is the k-step transition probability matrix, TPM. And what are its elements? P to the k, ijth element of that matrix is then nothing but probability XL plus K is equal to J given XL is equal to I. Okay? This is the probability that the L plus Kth state is equal to J while Lth state is equal to I. It is the probability that this state jump happens between I to J in K time steps. All right? Remember, if I substitute K equals to 1, this turns into the standard transition probability matrix, one-step transition probability matrix. So now we are going to ask some questions about especially this PK. Okay? We're going to ask the following questions. The first question is, does PK, so we see that this PK is nothing but a series. So I can increase K as much as I like, and I might wonder here, what happens when I let K go to infinity? Okay? What is going to happen when we increase time forever to this PK? Is this PK, is the state distribution, PMF of XK, is it going to settle at some constant vector? Or it's not going to settle? Is it going to diverge? Or is it going to oscillate, etc.? Okay? So we are wondering about the steady state behavior of this PK. Okay? So we are asking the question, does pk converge to a constant vector? Let me say p infinity. Okay? That is our first question. So we are asking if this limit as k goes to infinity, pk, is it, instead of pk I can write that formula, limit as k goes to infinity, p0 times p to the power k, is this limit equal to p infinity, a constant vector? So does p infinity exist? That is the equivalent question here. Okay? So this is the question of existence. Does p infinity exist? Does p infinity exist? That is the equivalent question. The second question that we are going to be asking is that if p infinity exists, is it unique? Is it unique and is it independent of the initial state distribution? Okay? So we see that this limit might depend on p0. Okay? So when this pk converges to this p infinity, if I change the p0 that I'm working with, is this limit going to change or is it going to remain the same? Okay, that is the second question. If p infinity exists, is it unique? Is it unique and independent of the initial state distribution p0? Okay? That is our second question. Of course, this is all going to depend on this matrix P to the K. Okay? So if you have taken the course EE557, you might remember the importance of powers of a matrix. Okay? In this case, you see that we end up with a power of a matrix again at the end, and investigation of these powers of a stochastic matrix is really a very, very important topic in the theory of Markov chains. Okay? So we are just going to see a part of that theory, and we are going to say that if these questions are answered with the answer yes, then we're going to have very nice properties of the Markov chain. So actually we are going to give a specific name if a Markov chain and its transition probability matrix would answer these questions as with a positive, affirmative answer. Okay? And that is going to be given in the following definition. If pk converges to a p infinity that does not depend on the initial distribution, p0, we call the Markov chain an ergodic chain. Okay? And this limiting distribution, the limiting distribution P infinity is called, there are many names. Physics people are working on Markov chains, or mathematics people are working on Markov chains. Control people might be working on Markov chains. Each one of these research areas, they would call this P infinity in a different way. So these different names are steady state, so I would say equilibrium, invariant, or stationary distribution. if for a Markov chain we can answer these questions with an affirmative answer, with a positive answer, if we can say yes, then we call that Markov chain an ergodic chain, okay? And we call this limiting distribution P infinity that would exist and that would be unique and independent of P0 as the steady state distribution or equilibrium distribution or invariant distribution or stationary distribution, depending on the area that we are working in. Okay? So then, what is the property of this ergodic chain? So in stochastic processes, ergodicity is one of the important topics, and it is related to the two different averages of the same quantity. Okay? So these are ensemble averages, these expected values, etc., and the time averages. If in a stochastic process, if the time averages would be the same as the ensemble averages, then we call that stochastic process an ergodic process. So here I would like to try to explain this under the framework of Markov chain. Let us say property of an ergodic chain. Okay? So in an ergodic chain, the time averages are equal to the ensemble averages. In other words, so I will try to explain this just a little bit. For the explanation, I would require the following function. The indicator function of xk equals to I. The indicator functions would be important in many fields, but here in probability, they have a specific importance here. So into an indicator function, in general, I can write here, this is indicator function of an event, okay? And this is equal to 1 if the event is true, event happens, okay? It is 0 if event does not happen. Okay? In general, therefore, into an indicator function, you put here an event, and the function becomes 1 if the event happens, and if the function becomes equal to 0 if the event does not happen. Here, the event that we choose is xk is equal to I. Okay? xk is equal to I. So this is going to be equal to 1 if event happens, that means xk is equal to I, and it is 0 if xk is not equal to I. In this manner, this is like an impulse function, okay? So with this event, this indicator function works as the impulse function, Kronecker delta function, delta xk minus I. If xk is equal to I, this is equal to 1. It's not Dirac delta. You have to be careful. It's Kronecker delta. Okay? So here I have, if xk is equal to I, then this delta becomes 1. And if xk is not equal to I, then we have the indicator function is equal to 0. Okay? Now we can actually express the following equality for an ergodic chain. Let me erase this part. In an ergodic chain, probability that xk is equal to I is equal to, this is the ensemble average, some form of, limit as n goes to infinity, 1 over n, I have k from 0 to n minus 1 indicator function of xk is equal to I with probability 1. So here I won't explain what this with probability 1. In the later parts of the lectures I will solve an example, and there I might actually try to show what this actually means. But this is, every equality has a meaning, and this is in general, there is a stochastic quantity here and there is a deterministic quantity here. Okay? So here, for this equality to hold, there are different considerations, and here for an equality to hold with probability 1 is one of the characterizations of these equalities. Okay? So here instead I will try to show you, forgetting about this, I would like to show you what this equality means. So here let us first try to understand this expression here. So I have a summation, and in the summation I am summing these indicator functions. Okay? I know that the indicator function happens to be equal to 1 if xk is equal to I, and I'm summing those results of those indicator functions. Okay? So this is the number of times the state xk visits state I. Okay? Between k equals to 0 and k is equal to n minus 1. Okay? So this summation is the total number of times that the state visits the state I. Okay? Because here this indicator function is 1 only when xk is equal to I. So in this summation I'm counting the number of times at which the state xk is equal to I between the time instance k equals to 0 and k equals to n minus 1. Okay? And then I am dividing this number with the total number of time instance. So this is the ratio of time instance at the number of time instance at which state is at state I divided by the total number of time instance. Okay? So this is the frequency of the state visiting the state I over the whole time instance. All right? And the right hand side is nothing but a probability. All right? So the left hand side is a probability and the right hand side is a time average. So what happens when I let n go to infinity here? The right hand side is that limit of this ratio, and the left hand side is the deterministic quantity which is a probability. All right? In an ergodic chain, this equality would always hold. This equality holds in an ergodic chain. So in order to be able to explain what this time averages being equal to ensemble averages means, I would write this probability in a different way. Okay? So here I can actually tell you that this probability is nothing but the expected value of the indicator function of xk is equal to I. Okay? And this is the ensemble average. Ensemble average. And this is going to be the time average. Limit n goes to infinity, 1 over n, k from 0 to n minus 1, indicator function xk is equal to I, with probability 1. And this is the time average. And in an ergodic chain, time averages are always equal to the ensemble averages. So you see that this is the ensemble average of this indicator function, and this is the time average of this indicator function. Okay? So then how are these two equal? This is not difficult to see actually. So remember, if I want to take the expected value of Cxk, then this is nothing but j from 1 to let us say I, Cj times probability xk is equal to j. Okay? It is this expected value. Now I can calculate the expected value of this function of xk. Expected value of indicator function of xk is equal to I is nothing but j from 1 to I, and here you see that in the first term in the summation we substitute j instead of xk. Okay, so in the indicator function I substitute j instead of xk. J is equal to I, okay, times probability xk is equal to j. So you see that this indicator function is only non-zero when j is equal to I, and that means that the result is going to be probability xk is equal to I. So these two are equal, and I say that these two are equal, and I write this because this looks like really an average of this indicator function, and this looks like the time average of the same indicator function. And in an ergodic chain, these two would be always equal. In the coming parts of these, maybe in the next lecture, I will actually try to show you an example Markov chain where this type of probability, this type of equality would not hold. And in that case, you might understand this in a better way. But still, this is a very, very deep idea that is in the foundation of stochastic processes, and it might be difficult to understand this idea without studying stochastic processes in more detail. Okay? So here, we ask some questions here. And the questions just were these. Does pk converge to a constant vector p infinity? It was the first question. Or does p infinity exist? And the second question was that if p infinity exists, is it unique and independent of p0? Okay? These were the two questions that we asked. And then we made a definition. This definition tells us that we answer these questions with the answer yes if the chain is ergodic. Okay? So the equivalent question that I can ask here, instead of asking those two questions, is this. When is a Markov chain ergodic? When is a Markov chain ergodic? Okay, that is my question. So we would like to understand when this pk converges to a constant vector, and when that constant vector is unique and independent of p0. And there is an equivalent question, a Markov chain in which we answer these questions with the positive answer. It's called an ergodic chain, so we can ask the equivalent question of when is a Markov chain an ergodic chain. Okay? So before I continue, actually I would talk about what happens when P infinity exists. Okay? So remember here our equations. We have found the equations pk plus 1 is equal to pk times p, and the second equation was just pk is equal to p0 times p to the k. All right? So now let us write a remark. suppose that P infinity exists. Okay? So I'm assuming that the first question is answered with the answer yes. Okay? In that case, what would be the properties that this P infinity should have? Okay? I know that this equality is satisfied for all case. Okay? For all case larger than or equal to 0, this equality is satisfied. So this means that limit as k goes to infinity, pk, if it exists, then I can say is p infinity. Okay? Then let me take the limit of both sides here. Limit of the left-hand side, if I let k go to infinity, would become p infinity. Okay? And if I let k go to infinity on the right-hand side, I would get p infinity times p. Okay? So you see that if p infinity, if the steady state distribution exists, then that distribution should satisfy its property. Okay? What does that mean? This is a horizontal vector is equal to the same horizontal vector times p. Okay? So remember the left eigenvector definition. A times L is equal to, I have L times lambda. This is the left eigenvector definition for a horizontal vector L here. Okay? And if I have this type of equation, what does it mean for the matrix P? I can write this equation as follows. P infinity times P is equal to P infinity times 1. So you see that, we see that P infinity has to be a left eigenvector. A left eigenvector of the transition probability matrix P belonging to the eigenvalue lambda equals to 1. Okay? So that is what our remark says. If P infinity exists, then that P infinity has to be a left eigenvector of the matrix P belonging to the eigenvalue lambda equals to 1. Do you think the matrix P, do you think it has an eigenvalue at 1? We have already seen this in the earlier lecture, and it was just this. Remember, P was a stochastic matrix, and if I multiply it with the vector 1 from the right, then I get the vector 1 here. But this is nothing but P times 1 is equal to 1 times 1. Okay? So we see that P has always an eigenvalue at lambda equals to 1 with the right eigenvector the vector 1. Okay? And this P infinity becomes the left eigenvector for the same eigenvalue. Okay? So you might remember here a matrix eigenvalues. I would have some eigenvalues for the matrix, and for each eigenvalue there exists a left eigenvector, which is the eigenvector of A transpose corresponding to the same eigenvalue, and a right eigenvector. Right eigenvector, they are the standard eigenvectors that we know. Left eigenvectors would satisfy equations like this. Okay? And we see here that the matrix P has always an eigenvalue at lambda is equal to 1, And the right eigenvector corresponding to that eigenvalue is the vector 1, and the left eigenvector corresponding to the same eigenvalue would become actually P infinity. It becomes the steady state distribution when P infinity exists. Okay? So here you can actually interpret this as follows. This P infinity is a horizontal vector. Take the transpose of both sides. Then the left-hand side would become P transpose, P infinity transpose, is equal to P infinity transpose. So a left eigenvector of A matrix P, is nothing but the right eigenvector of P transpose. And that is what you see here. All right? So P transpose times the eigenvector is equal to 1 times P transpose. So P transpose is the right eigenvector of P infinity transpose, is the right eigenvector of P transpose. That means that is the left eigenvector of the TPM capital P. Okay? So we see here, therefore, that this P infinity has a relationship with the eigenvalues and the eigenvectors of the matrix P, the transition probability matrix P. Okay? So an investigation of the eigenvalues and the eigenvectors of the matrix P might therefore be important in answering the questions that we have asked here. Okay? So this is the case always in control theory, in signal processing. If you're dealing with a matrix, an eigen decomposition or eigen analysis would be very, very useful. So here you see that I have pk is equal to p0, a vector times the kth power of the matrix P. Okay? So I know that if I apply an eigen decomposition or Jordan decomposition onto the matrix P, then I'm going to be taking the powers of the eigenvectors as well. When I take the powers of K, so let us say that P has the following Jordan decomposition. So I would have here Q times, let us say, the Jordan canonical form times Q inverse. Okay? This is the Q is the matrix containing eigenvectors and generalized eigenvectors in its columns, and I would have the inverse of that matrix, and I have the Jordan canonical form. And I know that P to the K is going to be Q times J to the K Q inverse. So I would be taking the kth power of the Jordan canonical form. So now let us look at this equation. When I actually take the powers of the matrix P, then somehow I will be taking the powers of the eigenvalues of P here in the Jordan canonical form. Okay? So if the eigenvalues of P, if they have a magnitude larger than 1, if they are outside the unit circle, as I increase this power, they are going to grow indefinitely. Okay? If there are eigenvalues of P outside the unit circle, when I take their power, they're going to fly away towards infinity. Okay? Can this really happen for this transition probability matrix? So what happens when we increase the power K here? Remember, answering this question, what happens when we let K go to infinity, is related to what happens to this matrix P as I increase the power K here. Okay? If the matrix P has an eigenvalue outside the unit circle, when I take its powers in the Jordan canonical form, then those eigenvalues would grow up. They would diverge away. Okay? So it's not really good for our purposes. So now that is what we are going to investigate first. We are going to look at the eigenvalues of the transition probability matrix P first. And we are going to have a very neat theorem claiming some important criteria about the eigenvalues of any stochastic matrix. Let us say theorem. Let P in Rn by n be a stochastic matrix. Just like the transition probability matrix. All eigenvalues lambda I in C satisfy, let us say, lambda I of P. Of P satisfy lambda I magnitude is smaller than or equal to 1. So we are told here that by this theorem, when I look at the eigenvalues of this transition probability matrix, when I look at the complex plane, they are either on the unit circle or inside the unit circle. Okay? So they are either on the unit circle, on this circle here, or inside. All right, that is what this theorem claims. So now let us give a proof of this theorem. Proof. So let lambda I be an arbitrary eigenvalue of P. Okay? Then I know that for any matrix, for any of its eigenvalues, there is at least one eigenvector. Okay? So let X be the corresponding eigenvector. Okay? So what does that mean? P times X is going to be the following: lambda I times X. I know that since X is an eigenvector, it's not equal to the zero vector. Okay? So this X is cannot really be the zero vector. All right? So this X has some elements, X1, X2, going until Xn, and not all of them can be equal to 0. So let me try to find the element of X with the maximum magnitude. Okay? So I will try to find maximum with respect to J of magnitude of Xj. Let us say that this maximum is achieved at the index J star. Okay? So the J star element has the maximum magnitude. Then this maximum is going to be maximum J, Xj is going to be Xj star. Okay? So now I have found some values here. I have defined the arbitrary eigenvalue, and then I have defined its eigenvector, and I have looked at its element with the largest magnitude. All right? And I know that, sorry, this is magnitude here, and I know that this should be non-zero. Okay? This largest magnitude has to be non-zero. Because if that largest magnitude is equal to 0, then the vector should be equal to 0. And I know that since it's an eigenvector, it cannot be equal to 0. Okay? So I know these facts. So now let me go back to this equation. Lambda I times x is equal to p times x. So now let me try to write this equation. Lambda I times x1, x2 going until xn is equal to, I have the matrix P here, and I have the vector x here. x1, x2 going until xn. So now I will here concentrate on the jth element or jth equation of this vector equation. Okay? Let me look at the jth equation of this vector equation. Lambda I times xj is going to be equal to this vector times the jth row of this matrix. But that is going to be this one. Pj1, Pj2 going until Pjn times x1, x2 going until xn. But this is nothing but a summation here. Okay? Lambda I times xj is equal to summation. I can here write, maybe I should use an index here, L from 1 to n, Pjl times xl. Okay? This is a vector equation. The left-hand side is a vector, right-hand side is a vector. A vector is equal to a vector. And now I'm looking at its jth component of this equation. It is lambda I times xj, the left-hand side. The right-hand side is the jth row of this matrix times this vector. It is this. And it can be written as a summation like this here. So now let me take the absolute value of both sides. When I take the absolute value here, when I take the magnitude, I can distribute this magnitude over this multiplication. Lambda I xj is equal to, L is equal to 1 to n, Pjl xl magnitude. So now I would like to take this magnitude inside. If I take this magnitude inside, then I would always get a larger quantity. Okay? So if I take this magnitude inside, the quantity that I get would always be larger than this number, because these can be positive, these xls can be positive, negative, or 0. When I take the absolute value of inside, I make this quantity larger at the end. So this is going to be L from 1 to n, Pjl, absolute value, and xl. This is actually nothing but the triangle inequality for the absolute value function. This inequality is nothing but triangle inequality. So now what I would like to do is that I would change this XL magnitude with the largest magnitude in the vector x. Okay? If I replace this magnitude with the largest magnitude in x, then this quantity would get larger. Okay? So I would put a smaller than or equal to sign. I would have L from 1 to n, Pjl, and I would have here xj star magnitude. Okay? So now this xj star magnitude, it is independent of the summation variable L. So I can take it outside. Equality. I will take the xj star magnitude outside. L equals to 1 to n. The transition probability matrix elements, they are either 0 or positive. Okay, so here I really do not need this absolute value here, right? So I can write PJL here. But here you see that I am summing the elements of the jth row of the transition probability matrix. So this sum has to be equal to 1. Okay? So that gives me, this is equal to xj star magnitude. So then what is our equation? Lambda I times xj magnitude is, I would have in the smaller than or equal to at the end, and I would have xj star magnitude. And this j was an arbitrary element. Okay, this is true for j from 1, 2, going until capital N. So I have this inequality for any j, any possible j. So if this inequality is correct for any j, I can choose j equals to j star. Okay? Then what would that give me? Lambda I xj star is smaller than or equal to xj star magnitude. And I know that xj star is non-zero. Okay? So it has to be positive, so I can cancel these from both sides. Then that would give me lambda I smaller than or equal to 1. So all of the eigenvalues of a stochastic matrix should be either inside the unit circle or on the unit circle. And actually, I know one of the eigenvalues. What is that eigenvalue? I already know one of the eigenvalues. Okay? And that eigenvalue is lambda equals to 1. One of the eigenvalues of the stochastic matrix is here. Okay? And the others can be inside the unit circle or on the unit circle, etc. But there is never an eigenvalue outside the unit circle for any transition probability matrix. This is actually quite good, right? So we don't have any eigenvalue with magnitude strictly larger than 1. So then when I look at this formula, pk is equal to p0 times p to the k, and when I write p in its Jordan decomposition, q inverse like this, then when I write p to the k, q j to the k, q inverse, then none of the terms here, the powers of the eigenvalues would not be diverging. Okay? Powers of the eigenvalues would not be diverging here in the Jordan canonical form. So here I will try to explain you what happens if I already know that there is an eigenvalue at lambda equals to 1. Suppose that this is the only eigenvalue on the unit circle. So, just an hypothetical assumption. Suppose that lambda equals to 1 is the only eigenvalue on the unit circle. And let us say that its multiplicity in the characteristic polynomial is 1. Suppose that the multiplicity of lambda equals to 1 in D of S is 1. So there is only this eigenvalue here with multiplicity 1, and all of the eigenvalues are inside the unit circle, okay, in the transition probability matrix. All right? So now I would like to explain you what happens in that case to this P to the K. In that case, I can write the Jordan canonical form as follows. In the Jordan canonical form, there is going to be a 1-by-1 Jordan block belonging to this eigenvalue. Okay? And all of the other eigenvalues will have other Jordan blocks. Let us say that this is the Jordan canonical form of the rest. All right? I know that all eigenvalues of this Jordan canonical form of the rest would be inside the unit circle. Okay? So then what is going to happen when I take the power j to the k? In that case, I would have this 1 is going to remain there because 1 to the k is 1, and this Jordan of the rest is going to be taken the power of k. We have seen in the earlier parts of this course, if a matrix has eigenvalues all inside the unit circle, then when I take the power of that matrix to the power k, and when I let k go to infinity, that matrix should go to 0. Okay? So what is going to be limit as k goes to infinity, j to the k? It is going to have the following form. This 1 is going to remain here, and the rest is going to be equal to 0. I would have 0, 0, 0 here. Okay? So when Jordan canonical form, when I take its power, when 1 is the only eigenvalue on the unit circle, and when the multiplicity of 1 is 1 in the characteristic polynomial, then when I let k go to infinity, the Jordan canonical form to the power k is going to go to this matrix. Okay? So here now let me write P to the k. P to the k is Q times j to the k times Q inverse. Okay? Take the limit as k goes to infinity. In that case, this is Q. Let k go to infinity, it's going to be this matrix. 1, and everything else is 0. Okay? And I have Q inverse here. So then what is the structure of Q? Q in its columns contains the eigenvectors and the generalized eigenvectors. Okay? So I have here the eigenvalue 1. So in its first column, we are going to have in the first column of Q, we are going to have the eigenvector of the matrix P belonging to the eigenvalue 1. But I already know that eigenvalue. I already know that eigenvector. P times 1 is equal to 1 times 1. So the eigenvector of P belonging to the eigenvalue 1 is the vector 1. Okay? So the first column of Q is going to be 1. And I don't really care about the rest at all. Okay? We will see why. And I would have here 1, and the rest is equal to 0. And here, I will only consider the first column of Q inverse. First row of Q inverse. I will call that first column, first row. I'm really sorry. My brain is running out of its power. So I have a Q inverse here. I will call its first row as pi, and I won't care about the other rows. All right? So I really do not care. So then what is going to be this multiplication at the end? Okay? So this multiplication, if I do it with the partition matrix rules, if I apply this partitioning and if I do this multiplication, I'm going to get the following. This is going to be 1 times the vector 1 times the vector P. Okay? This one, it is not really important. I really do not have to write it there. But this vector 1 is just this. 1, 1, 1. It's all ones. And this P happens to be having elements P1, P2 going until Pn. Okay? What would happen when I make this multiplication? The result would be the following. The first column would be P1. The second column would be P2. P2. The last column would be Pn. This is a rank 1 matrix, and you see that all rows of this rank 1 matrix would be equal. Okay? So you see that when the eigenvalue 1, when it is not repeated, and when it is the only eigenvalue on the unit circle, okay, when I let pk, p to the power k, when I let k goes to infinity for p to the power k, I would get a matrix which would have equal rows, okay? And all of these rows are equal to this pi vector, okay? All of these vectors, all of these rows would be equal to pi. Now I'm wondering about what that vector pi might be. Okay? I will go back to the following case. I know that P is Qj Q inverse. Okay? In the course 501, I always turn this equation into the following form. I always write it in the following form. P times Q is equal to Q times J. Okay? And what is this? P times the columns of Q, let us say Q1, Q2, going until Qn. And let us say this is Q as well, Q1, Q2, Qn. And let me say that the Jordan canonical form is diagonal. Okay, I don't care now. So let us say that it's diagonal, lambda 1, lambda 2, going until lambda n. So now what does this equation give to me? It gives to me P times Qj, the columns of. So when I do this multiplication, this is going to be the multiplication of columns of Q with P. P times Qj is equal to lambda I, lambda j times Qj. When I multiply a diagonal matrix with another matrix, when I multiply a matrix with a diagonal matrix from the right, I just weight its columns with the corresponding diagonal elements. So this is weighted by lambda 1, lambda 2, lambda n. Okay? So, and when I do this multiplication, I would have P times Q1 in the first column, P times Q2 in the second column, etc. So when I equate the jth columns of the left and right hand side, I would get this equation. Okay? So I see that the columns of the matrix Q, when the Jordan canonical form is diagonal, the columns of the matrix Q are eigenvectors. Right eigenvectors of the matrix P belonging to different eigenvalues. So the columns of Q are the right eigenvectors. All right? Now I will interpret this equation in the following way. Instead of taking this Q inverse to the other side, I will instead take this Q to the other side. Okay? So it's going to give me Q inverse times P is equal to J times Q inverse. Okay? So this is just the same equation but interpreted in a different way. Now instead of looking at the columns of Q, I will look at the rows of Q inverse. Okay? Let us say the rows of Q inverse are R1, R2, going until Rn times P is equal to diagonal matrix lambda 1, lambda 2, lambda n times Q again. Okay? Q inverse again. R1, R2, going until Rn. Okay? Now what I would like to do is to look at the jth row of this multiplication. Okay? Jth row of the left hand side would be Rj times P. Okay? By the partition matrix rule, jth row is going to be Rj, the jth row of this matrix times P. And the jth row of the right hand side is going to be lambda j times Rj. Okay? So because when you multiply a matrix with a diagonal matrix from the left, we just weight the rows of that matrix with the diagonal elements here. So the jth row of this multiplication would be lambda j times Rj. Okay? So now what is this equation? When I multiply this row vector with P from the right, I get a multiple of the same row vector. Here, compare this one with this one. Okay? So here, I see that Qj is a right eigenvector of P. Okay? And what do you see here? 4 lambda j. 4 lambda j. And what do you see here? Rj is the left eigenvector of P 4 lambda j. Okay? So I will write here Rj is the left eigenvector of P for lambda j. So here what do we see? We see that if the Jordan canonical form is diagonalizable, is diagonal, then the columns of Q are right eigenvectors of P. In the similar case, rows of Q inverse are left eigenvectors of the same matrix for the same eigenvalue. Okay? So here, let us go back to here. This one vector was the right eigenvector for the eigenvalue 1. And it is the first column of the Q matrix. This is my Q matrix. And this is the Q inverse matrix. Okay? And the first row of it, this pi vector is going to be the left eigenvector. Pi is the left eigenvector of P for lambda equals to 1. Okay? So this pi vector where this limit P to the infinity matrix is going to have in its rows, this pi vector is nothing but the left eigenvector of P for lambda equals to 1. Okay? So what does that mean for pi? Look at this equation. Pi times P is equal to 1 times P. But that is our recursive equation. Pi equals to pi P. Okay? So this is like an equation, P infinity is equal to P infinity times P. Okay? So here we saw something very important. We saw that all eigenvalues of P are actually either on the unit circle or inside the unit circle. Then we made a hypothetical assumption. This hypothetical assumption was that, suppose that lambda equals to 1 is the only eigenvalue of P, the matrix P, on the unit circle, and suppose that it is not repeated. Okay? In that case, I showed you that when I let K go to infinity, the matrix P to the power K is going to converge to a matrix where all rows are equal. And these rows are actually nothing but the left eigenvector of the matrix P belonging to the eigenvalue 1. Okay? So then what happens if these hypothetical conditions are not satisfied? Okay? Remember, when I take the power of the Jordan canonical form, I told you that when K goes to infinity, it's going to turn into this. I know that if there are more eigenvalues at 1, or if there are more eigenvalues of P on the unit circle, then the shape of the structure of the Jordan canonical form when K goes to infinity will not be in this form. Okay? So in that case, there might be multiple eigenvectors for the eigenvalue 1, or there might be other terms here on the unit circle which would give us trouble. Okay? So all of the Markov chain theory that we are going to see in this course is going to be done in order to be able to assure that the Jordan canonical form of the P matrix is in this form. Okay? If it is in this form, then we can answer the questions that we started with an affirmative answer, with an answer yes. Okay? And in that case, the state distribution of the Markov chain is going to converge to a stationary distribution, steady state distribution. And then the Markov chain is going to turn into a stationary stochastic process. Okay? So in the next lecture, we are going to see some conditions, some sufficient conditions that would assure that this Jordan canonical form of the P matrix, the transition probability matrix, is in this form. Okay? But that's all for this lecture. Thank you very much for watching. Bye.